Okay, so let's practice assigning polarity to molecules. So again, there are two different types of polarity. There's bond polarity, where there's a separation in charge based in different electronegativities of an atom in a covalent bond. So we can determine if a bond is polar by subtracting those electronegativities and seeing if it's greater than 0.4 or not. Molecular polarity is looking at all of the vectors in a molecule to seeing if it sums to zero. If it sums to zero, it's nonpolar. And then if there is a vector, it is polar. So what we're going to do is we are going to use this Vesper practice sheet that we used to practice drawing the molecular geometries of each of these. And now we're going to go through and tell if each is polar or not. So this carbon tetrachloride we did already. So now I'm going to draw the vectors on this picture. We just did this one too. So it's pointing towards the carbon, because remember, these vectors point from the less electronegative to the more electronegative. These vectors, because this is in 3 dimensions and each of these are 109.5 degrees, this is going to equal 0. So there is no net vector, so this is non-polar. This is a non-polar molecule. So now let's look at this nitrogen trihydride. Nitrogen is more electronegative than hydrogen. So we're going to draw these 3 vectors from hydrogen to nitrogen. These 3 vectors are equal in magnitude. They are not going to cancel each other out. They are going to give a net vector somewhere in this direction. This is a polar molecule. Let's look at carbon dioxide. Again, remember, we are only drawing vectors on molecular geometries, not on Lewis structures. So here, oxygen is more electronegative than carbon. So this would be what the vectors look like. This is a linear molecule. These are equal magnitudes and opposite directions. This is a non-polar molecule. How about oxygen? So we weren't able to name this. It's a linear molecule. It's flat. Oxygen, it doesn't matter which way you draw these vectors. You could draw them this way, or you could draw them this way, because they're the same electronegativities. So it's not like one is stronger or one is weaker for you to show which way these arrows go. The point is, there is no net dipole because these are 2 of the same element. So this is also a nonpolar molecule. This is really important, especially in biochemistry. If you ever take any biochemistry classes, we have a molecule in our blood called hemoglobin, and the whole job of hemoglobin is to transport oxygen. And I always ask a question on my biochemistry exam: why do we need a molecule to transport oxygen? And almost all of the time, people can't think of why. The reason we need a molecule to transport oxygen is because our blood, our bodies, are mostly an aqueous solution. Aqueous means we are dissolved in water. Water, we have already said, is polar. Oxygen is nonpolar. Polar things and nonpolar things do not mix. We're going to get to that next when we start talking about intermolecular forces. So because this oxygen is in a polar environment, it needs a molecule to carry it around, because polar and nonpolar don't mix. Carbon dioxide, same thing. So during cellular respiration, we use oxygen, and then we produce carbon dioxide as a byproduct. There is no molecule that carries carbon dioxide around, but what happens is there's something called a buffering system that converts this carbon dioxide into something called carbonic acid. Carbonic acid is polar, and carbonic acid, because it is polar, it can diffuse in our aqueous blood till it gets to our lungs and can be exhaled. So that's just a little bit of biochemistry here. Polarity is really important in almost every part of chemistry. So just a heads up for that. Okay, so let's keep going. Here's our arsenic trifluoride. So we are drawing vectors. Fluorine is the most electronegative, so we're going to draw vectors towards the fluorine. Again, these are equal in magnitude, but not in direction. So there's going to be a net vector in this direction, which means this is a polar molecule. Here, sulfur dioxide, these are equal in magnitude, even though this has a double bond here. Remember, this is a resonance structure where this double bond is really like vibrating back and forth, existing in both of these positions. So the size, the magnitude of the vector is the same here. So I would say oxygen is more electronegative because of the trend. So we would draw like this, like this. There is a net vector in this direction. So this is a polar molecule. So one thing that you should be able to do in this chapter, we're kind of building. First, we learned how to name molecules. From the name, you should be able to write the formula. From the formula, you should be able to write the Lewis structure. From the Lewis structure, you should be able to tell the steric number, the electron pair geometry, and the molecular geometry. You should be able to draw the molecular structure, and then you should be able to assign vectors to tell if this molecule is polar or not. In the next chapter, we're going to talk about something called intermolecular forces, and knowing if a molecule is polar or not is going to be very important. So all the way from back in chapter 3, we're going to need to use all of these pieces of information to answer these questions.